Hello everyone, I'm Michael Frank, and this is the introduction to technical session 1 on fundamental physics issues in the CCC workshop on physics and engineering issues in adiabatic and reversible classical computing. By the time you see this, I will hopefully in the workshop introduction have already shown this outline of the workshop schedule. So of course we are on day 1. I'm doing a double length plenary video to introduce this session, and then we will have at least 3 more talks in this session, possibly one more if we can find a substitute for Craig Lent, who unfortunately was not able to provide the video for his material. And then in the afternoon, we're going to have a breakout group meeting for the group of folks that are interested in fundamental physics issues and who have position papers that they'll be presenting on this topic. And then days 2 and 3 will be additional topics, which I'll introduce on those days, and then we'll have working meetings on days 4 and 5. This is a talk abstract, and it's not good form to just sit and read some text, but you can always go back and review this video offline if you want to read this. But the upshot of it is that the question of how efficient reversible computing can be has never been satisfactorily answered, and part of why Tom and I organized this workshop is to help impel the physics community to begin seriously working on these issues. So just as an outline, I'm going to start with some motivation and some very brief history of this subject, and then I'll go through some material on a number of foundational topics. We'll take a break about 20 minutes in so that we can, I don't know, just slice up the video a little bit so it's not just one big chunk. And then I'll close with some comments on future directions, which I'll also talk about a little more during the breakout session. So we'll start with motivation. So of course the whole motivation for this field from my perspective is that there's a serious problem that the energy efficiency of conventional computing technology is approaching some pretty unavoidable limits that trace back to fundamental thermodynamic issues. And this is important because if we can't increase the energy efficiency of computing at a fundamental level, then there's going to be diminishing returns from every other way in which we try to improve computing technology. Eventually we'll have optimized everything that can be optimized, and we'll be facing hard limits on future gains in overall computer system efficiency that follow from limits on fundamental device and circuit level characteristics. I'm going to present the argument that the only way around this problem is to adopt this alternative computing paradigm that we call reversible computing. And there are some very strong reasons from fundamental physics as to why this is really the only possible way that general digital computing can continue improving in efficiency after the limits of the conventional approach are reached. So this has enormous long-term implications. So, the whole economy depends on computing these days to an increasingly large extent, and this trend will probably increase in the future. So by improving the performance of our computing systems, within any given constraints on system power and so forth, we're also indirectly, we're improving the total economic value of our civilization that'll become increasingly dependent on computing. So just briefly as to why the conventional approach is reaching its limits. If you look at the semiconductor roadmaps, they tell you what the characteristics of minimum size transistors are. And if you calculate from those how much electrostatic energy is stored on the gate of a turned on transistor, you find that by the end of the roadmap, which is about 2030, we're getting down to the range of a handful of electron volts, at which point thermal noise starts to become noticeable. And if you tried to push much lower than that, you would find that the characteristics of the device would be greatly degraded by the fact that thermal noise is sufficient to allow electrons to hop across the potential energy barrier represented by a section of a turned on or turned off transistor gate, right? So transistors essentially no longer are able to turn off adequately once the gate energy gets that small. But the problem is, even worse than that, the actual electrostatic gate energy is only a tiny fraction of the total electrostatic energy stored on a logic node. In other words, a segment of conductor that's connecting several logic gates. And if you multiply together all the overhead factors that you typically have in high performance logic, it's pretty substantial. It's about a factor of 500, give or take, a factor of 2 or 3. And so you find that even though the energy on the minimum size transistor gate itself might only be a few electron volts, you find that the total electrical energy on a circuit node is more like a kilo electron volt. One way to think about that is, it's one electron or a few electrons is just not enough to occupy an entire circuit node, which is an extended piece of conductive material. And so you end up with relatively large numbers of electrons at whatever voltage they're at, which might be around a volt. And so you get a KeV sort of typical energy scale at the end of the CMOS roadmap. And this might be improved a little bit, but it's not going to improve by orders of magnitude. So basically the traditional semiconductor industry is stuck. It's not going to be able to get beyond these kinds of limits, maybe 500 EV if they're lucky. But if you use reversible computing techniques, in principle, they can save all of this energy. Whoops, I skipped ahead. Save all of this energy. And as far as we know, there's no fundamental limit to how low the energy dissipation per operation for reversible operations can go. So people say, oh, we're still far from the Landauer limit, which I'll talk about. So why do we care about reversible computing? Well, no, we can save energy even from the point we're at now by doing things reversibly. We don't have to wait until somehow we approach Landauer, which we'll never do with conventional circuits anyway. We don't have to wait till we get so close to that with conventional techniques before we start using reversible computing. It's already useful. And I'll explain that more tomorrow in the technology intro lecture. So, why is this important? Obviously, if you can't improve the energy efficiency of computing, then there will always be a lower limit on power dissipation required for any given level of performance. And so there's this entire infinite plane of power performance characteristics that we'll never be able to get to if we don't do reversible computing. And in fact, you know, the practical limits are actually fairly close, to the extent that we probably will never have supercomputing systems at a zettaflop level of performance within reasonable power constraints. Incidentally, you know, arguably there are distributed computing systems that already have zettaflop scale performance, like the Bitcoin network, for example, but of course the power dissipation is also very large and distributed in those types of systems. So now let's talk a little bit about some foundational theory, because that's what this technical session is about. And I'm going to present a very simple general view of the fundamental physics of reversible computing, and this will be elaborated upon by subsequent speakers who have their own perspectives on this topic. But what I'm presenting here is just sort of to lay some groundwork and establish some sort of common language. You know, I'll start by talking about what a computational state is in a physical sense, and how we can understand it in a sort of quantum mechanical representation. And then I'll talk about what I call the fundamental theorem of the thermodynamics of computing, which relates computational and physical measures of entropy. And it turns out they are related fundamentally in an unavoidable way. And so then we'll talk about notions of computation and computational operations. Then we'll take our brief break, and then I'll talk about Landauer's principle, which I claim is widely misunderstood, including by a lot of people in the physics community. I think that some of the more computational or information theory aspects of Landauer's principle are not taken into account in some treatments that it has received in the thermodynamics literature. And so I'll try to clarify that for everyone. And then we'll talk about how you can model classical computation in a quantum framework and what it means for the time evolution of a quantum system to implement a classical computation. I'll also talk about relations between speed and dissipation, and then you know, what has been done on that in the past, and that will lead into the next part of the talk, which is about future directions, which is basically to improve the theory of the limits of reversible computing. So we start with a general non-equilibrium open quantum system framework. This is just a very simple picture. Some versions of this have an external power supply, but you know, for simplicity, we're just going to say the power supply is integrated into the computing system. It could be a battery or a tank of gas fueling a generator or anything you want. You know, we're not really going to care about that so much, but for our purposes, it is helpful sometimes to talk about a flow of heat out of the computing system to an external environment. And we'll make some typical simplifying assumptions where, you know, we can assume that the Hilbert space of this whole model universe can be factorized into separate Hilbert spaces for the computing system and the environment. And we'll also assume that essentially any correlations that might arise between the computing system and the environment are going to be quickly lost after some thermalization time scale. So in other words, after a short time, our model of the system will be sort of a factorizable a tensor product of a density matrix for the system and the density matrix for the environment. And you know, that's important because that's essentially our fundamental mechanism of entropy increase, that the computing system evolves unitarily and the universe as a whole evolves unitarily in an ideal perspective, but because we can't track the correlations between the system and the environment, we take a simplified view as modelers. And if you force the model of the system into a factorizable state, you're increasing the von Neumann entropy that you would have if you could track the whole entangled state of the system. So, if you trace out the environment, for example, you're increasing the von Neumann entropy compared to if you don't do that disentangling type of operation. So it's kind of a standard perspective on decoherence, in other words, that we're taking here, and entropy increase. Now, it's going to be important for our purposes to talk about what a computational state is. And remember, these are classical computational states. We're not going to care about superposition states like we do in quantum computing, although a proper theory of thermodynamic limits of reversible computing ought to be able to be extended to the quantum case. But we're just starting with the classical case for now, because that's what's important for improving the energy efficiency of sort of general digital computation, which is our goal here. So we're just going to treat initially computational states are just atomic entities, abstractions, okay? And there's some set of possible computational states. And if the system is not in any of the defined computational states, we'll just say it's in some dummy state or catch-all state. And so we can talk about an extended set of computational states that includes the catch-all state. And this is needed because when you talk about physical systems, obviously it's going to be possible for the physical state of your computer to be messed up in some way that it doesn't actually represent any valid computational state. So that's what this bucket is for. So now for the connection to quantum theory, we're going to do something extremely simple. We're just going to say that there exists some basis for the Hilbert space of the system, the computer system, such that if you were to measure the state of that system in that basis exactly and project it all the way down to one of the orthonormal basis states, if you chose your basis appropriately, then from that resulting state, you could tell with certainty exactly which computational state the system was in, or if it wasn't in any valid computational state, then you could say with certainty, oh, it's in this other invalid state. So this is nothing new. In fact, Shane did something essentially the same as this when he defined his notion of digital states when he was developing his theory of channel capacity and limits of fundamental communication. And it's a very natural representation, because the intuition is that whatever quantum state your computer might happen to be in, if you could measure it precisely in an appropriate basis that corresponds to the way you break down your description of the system into computational states, then you could tell what the computational state is, at least in principle. So this is going to be our sort of starting point for this theory. And there's maybe room for debate about whether that's the representation, and that could be a topic for the breakout session. But I'm going to argue that this is the right definition to start with. So then, now let's drill down a little bit. we have a computer system which has, you know, many interacting physical parts in it, circuit components and so forth. And we're going to sort of break down the degrees of freedom of that system into what we call the computational subsystem, which are just the classical bits themselves, and the non-computational subsystem. And, you know, we're going to pretend for most purposes that this factorizes. Even if it doesn't, you can still represent the Hilbert space for the whole system as a subspace sum of subspaces for the non-computational subsystem that are dependent on which computational state you are in. So this is a very general here and can probably apply to any real system. I owe thanks to Carper for pointing this subspace sum representation out to me. I think it's you know, sort of an elegant way to avoid making this factorizability assumption. So, all right. Now, everything I've done so far in terms of having what I call this proto-computational basis that we use for defining the computational states, all of this could in principle be time dependent, because as you know, your physical mechanism that is your computer is evolving over time. The representation of the computational states can also be evolving. So, for example, if you're representing a bit with a pulse of, you know, on a transmission line, or you know, we work with superconducting circuits in one of our projects at Sandia. But if you have a, you know, some sort of moving pulse, then, you know, your basis might be such that, you know, if you measure the system in a certain basis, you can tell from the state of that pulse whether it's representing a 1 or a 0. But since the pulse is moving along, the appropriate basis for measuring it would also in general be changing. And, you know, this applies to any of the degrees of freedom in the computer that are actively representing information. They will in general be evolving in time, and so the way that we interpret the physical states as computational states will naturally be evolving along with the system itself. So, you know, I'm not going to talk about this elaboration of the notation very much. It's just enough for now to know that we can, in principle, always define things this way if we want to treat the dynamics of, say, a nano device that we're using to represent information. Oops, I skipped ahead too far. Now, here's a very simple statement, which I call the fundamental theorem of the thermodynamics of computation, because it is pretty central to this subject. And some people think of this as Landauer's principle, but, you know, I'm going to argue that the important meat of Landauer's principle is really a different statement from this. And so that's why I just call this the fundamental theorem. All this is the observation that, you know, given that we're defining computational states as set of physical states, you can always define a probability for the computational states. It's just simply a sum of the probabilities of the physical states that make up that computational state. And so this is what fundamentally connects, you know, probability distributions from a perspective of computation or information to probability distributions that we have in statistical mechanics for the microstates. And if you, you know, just make this observation that this is what the probability computational state is, it's very easy to then derive that the total entropy of the physical system, which we saw on this slide here, the computing system, it can always be expressed as simply a sum of the Shannon entropy of the computational state plus the conditional entropy of the physical state conditioned on the computational state. And I call this the non-computational entropy. And, you know, because of this, you find that computational entropy and physical entropy that is not computational are kind of interchangeable in the sense that the boundary between these two terms depends entirely on where you draw the boundaries of your computational states back in this picture, right? So if you left the basis states the same, but you just redrew the boundaries of your computational states, you would find that the terms were different now in this expression here, but the sum would still be the same because it only depends on the probabilities of the physical states. And so this ends up relating to the way that entropy can be transformed between computational and non-computational forms in physical systems. And that's in itself a reversible process, but Landauer's principle, I will argue, is something different, which is not reversible, and we'll get to that in a minute. This is just another version of the same statement. Here we're just drawing it on that diagram where we view the computational subsystem as a part of the whole computing system. And the non-computational entropy is just the total entropy minus the computational part. So this is all very simple so far. Next, before the break, just a few definitions. We're going to talk about computational operations, which are essentially just transformations of computational states. And, you know, most generally, we can take these as stochastic operations. So we get a whole probability distribution over final states. And of course, you could generalize this further to quantum operations, although we're not going to do that for purposes of this talk. And then, you know, there's the concept of reversible operation, which, you know, a simple way to define that is it just means that every final state is only reachable from at most one initial state. So you never have non-zero transition probabilities from two different initial states to a given final state. And, you know, we can also elaborate on this definition a little bit. We can say that an operation is reversible under some precondition that the initial state is in a restricted set. And this may seem like an ad hoc thing to do, but this is actually key for building physical mechanisms to do reversible computing, because usually the simplest mechanisms are ones that assume some precondition holds and transform the state reversibly under that assumption. And so these turn out to be actually a more practical foundation for real hardware than the normal kinds of unconditionally reversible operations. And finally, you know, that concept we just introduced can also be made time dependent. So you can talk about a computational operation that applies between two times. So it takes some finite amount of time to occur, and it is operating on the notion of computational states that you have at the two times in question. So, you know, this allows that operation to be implemented over time in a physical machine that is itself changing over time, and the interpretation of the states can be changing over time and so forth. Okay, so that's going to be the stopping point for the first part of the talk, and I'll stop here just to allow that to be packaged up as a recording, and then we'll go to the next part.